Welcome to Lesson 3E, Differential Linear Momentum Equation. In this lesson, we'll derive the differential linear momentum equation by using the control volume form of the equation and applying Gauss's theorem. We'll also talk about conservative versus non-conservative forms of the equations, and we'll talk about Cauchy's equation. Let's start with the control volume form of the linear momentum equation that we derived in the previous lesson. There are two volume integrals and two surface integrals, but we'll use Gauss's theorem to convert these two surface integrals into volume integrals. This is Gauss's theorem for a general property phi. Consider this integral first. We'll choose this grouping as our capital phi, and Gauss's law tells us that this integral is equal to the control volume integral of del xj of phi dv. We can use control surface and control volume instead of V and A, since the area here is defined as the area that bounds or defines the volume, and the same thing is true here. Likewise, this surface integral, by Gauss's law, is an integral over the control volume, del xj, of the stress tensor Tij dV. Now let's combine all these terms under one roof, so to speak, like we did with the conservation of mass equation. We have integral over the control volume of the unsteady term del t rho ui. I'll save my dv to the end. We have this term as our second term, and I'll put a bracket around this whole thing. This third term will be put on the left-hand side, so it becomes negative. And the fourth term will also be put on the left-hand side, but we'll use this volume form, close the brackets, and put our dv on the whole integral. Since we put everything on the left, the right-hand side must be 0. Now we make the argument that for any arbitrary control volume, the integrand, all these terms that I'm circling, must be 0, so that the integral of all those terms for any arbitrary control volume, no matter what its size or shape, equals 0. Thus we can write the differential form of the linear momentum equation. Basically everything encircled in red has to be 0. We typically put these two negative terms back on the right-hand side, giving us this equation, which is our differential linear momentum equation. I typed it up here. Notice that the j's are summed in these two terms, and I is a free index in all of these terms. So this is a vector equation. I repeat the equation here, and I want to talk about conservative versus non-conservative forms.
I am always very conservative.
My parents were conservative, but I lean more liberal. No, guys, we're not talking about politics here. This equation is what we call a conservative form. There are two reasons we can say this. First, it was derived directly from the integral conservation form using Gauss's theorem. And second, which is easier to spot, none of the variables being differentiated appears as a coefficient in another term. For example, we're differentiating rho. Rho doesn't appear as a coefficient out here in any of these terms where there's derivatives. To make this more clear, we're only talking about terms where there are derivatives. This term doesn't count, for example. Similarly, velocity vector ui is differentiated, but it doesn't appear as a coefficient in either of these two derivative terms or in this term. For example, consider this second term. Using the product rule, we could write this as rho uj del ui del xj plus ui del rho uj del xj. This form is conservative by our second rule, and these terms are non-conservative. Again, by this rule, velocity is being differentiated here, but it also appears as a coefficient in this term. Likewise, rho is differentiated here and appears as a coefficient here. Let's talk about conservative forms and non-conservative forms more generally. Let's let capital psi be some property, where psi is the conserved property. For example, mass. Lowercase psi is uppercase psi per unit mass. Therefore, rho times lowercase psi is uppercase psi per unit volume. For example, if capital psi is mass, lowercase psi is mass per mass, or 1, and rho psi is just rho. We can write a general conservative form of the differential equation for conservation of this property psi, namely del t of rho little psi plus del xj of rho uj times little psi. equal, and then we put sources on the right. We call this the conservative form because of rule number 2 that I mentioned previously. This psi is the conserved property per unit mass. Again, because of these sources, psi is not truly conserved, but we call this the conservative form of the equation. Again, we'll use mass as our example, where mass is truly conserved. As we mentioned up here, for mass, psi equal 1. So this equation becomes del del t of rho plus del del xj of rho uj equals 0. So this would be our differential equation for conservation of mass in conservative form. Now consider the momentum equation. We'll let uppercase psi be the momentum, which is mass times velocity. So lowercase psi, which is momentum per unit mass, is just the velocity. And the equation we had before is repeated here, our linear momentum equation. By comparing with this general conservative form, we see that this equation is in conservative form. To convert this to non-conservative form, we use the product rule. We split it up to rho del ui del t plus ui del rho del t, and the second term is also split up into rho uj del ui del xj plus ui del del xj of rho uj. Let's rearrange, combine the two terms with rho and the two terms with a ui in front. But something nice happens here, namely that this grouping of terms we recognize as the left-hand side of the continuity equation, so the encircled terms are equal to 0. We also recognize these two terms as the material derivative. Thus the entire left-hand side becomes rho dui dt, material derivative, and then the terms on the right side remain unchanged. This is thus the linear momentum equation in non-conservative form. These equations are equivalent since all we did was use the product rule and the continuity equation. The difference typically comes when you're doing computational fluid dynamics, where the conservative form is often preferred, but there are cases where this form is more useful. This differential equation in non-conservative form is called Cauchy's equation, and I typed it up here. Cauchy's equation is valid for any fluid, compressible or incompressible, Newtonian or non-Newtonian, and even for solids. The distinction between these comes from this stress tensor. So the next thing to do, which we'll do in the next lesson, is to ask this question: how is the stress tensor Tij related to primary variables in the flow? That is velocity, pressure, density, and other fluid properties like viscosity. In the next lesson, we'll come up with an expression for Tij in terms of these primary variables for Newtonian fluids. One final comment, and I said the same thing when we derived conservation of mass. You could also derive Cauchy's equation by looking at a small fluid element and letting it shrink to 0, summing all the forces on the fluid element and these faces, and using truncated Taylor series. This is how you may have seen this equation derived in your undergraduate class. Here we derived Cauchy's equation in a much more elegant way.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.